Hello and welcome to Cup of Cosmology, the place for all your questions about the universe. My name is Diana Hooper and I'm a postdoctoral researcher currently at the Helsinki Institute of Physics over in Helsinki in Finland. And I'm a cosmologist, so that means that I study the universe, the contents of the universe, how everything evolves, how everything interacts, all of the cool things happening inside the universe. It's really, really fun. I love that I get to study stuff happening in the universe and talk to you all about it. And yeah, I love chatting about the universe, cosmology, science, research in general, academia, a lot of ranting when I do that. And purpose of Cup of Cosmology is for me to come and tell you everything you want to know and everything you never knew you wanted to know about the universe. So as always, this is an interactive stream. This relies on everyone asking questions. So as always, jump in and ask all of your questions. And hello to all of the regulars joining in the chat. I see we have Scott, we have Paul, we have the two Davids here. Great to see you all. I see some of you already posting comments before I went live because I was just distracted making tea and here on time. So thank you everyone for joining. As always, hey James, great to see you as well. So if you're a first-time viewer, welcome. If you're a regular or a repeat viewer, welcome back. Great to have you all here. If you haven't yet subscribed to the channel, please do so. Click the subscribe button, leave a comment, like the video, all of the usual YouTube things. It really does boost the viewership, and I do appreciate you all taking a second out of your lives to click the right buttons on YouTube for me. You missed the last stream, not to worry. The streams are always uploaded on YouTube, and it's not like there's a to-be-continued storyline advancing here. It's not like you have to tune in every week for the plots development. There's no real plot development. These are standalone episodes, so you can come in and leave as you please. There's never any obligation, but great to have you here this week. Tea currently at 350 Kelvin. Tea currently is too hot to drink. Tea will be too hot to drink for the next 20 minutes probably. But yes, I developed the annoying habit where 20 minutes before I'm set to go live every Sunday without fail, I find something that completely distracts me and then have to do a last minute mad rush, like 5 minutes to 8. It's like, oh, I'm going live in 5 minutes. I haven't set up anything. On that note, I've just realized that I might even be using the wrong microphone currently. So let me just check that you are all hearing the microphone correctly. Yes, okay, microphone is the correct one. Excellent. This is what happens when I get distracted 20 minutes before I go live and then have to set everything up very, very, very quickly. Okay, so just checking that I didn't miss any important comments here. I see you all saying hello. David Dunn giving a spoiler of what we're going to talk about today. Happy 23-hour long day to those who celebrate. Yes, a lot of us changed our clocks this week. Some of you already did it 2 weeks ago. This is a ridiculously stupid thing. Daylight saving time is something that makes no sense scientifically. It's something that should be abolished. We should not be doing daylight saving time. This is my every 6 months I do this rant, and someday maybe I will be able to stop doing this rant when we finally realize that it's an antiquated thing that we do not need to do. Yes, we did indeed switch to daylight saving time today. That's why if you haven't switched your clocks, the stream is 1 hour earlier than what you're used to. If you already switched your clocks 2 weeks ago, we're now back in sync. So yes, daylight saving time is ridiculous. You know, it would make a lot more sense to just keep winter time all year round, but at this point, I don't care which we keep. We just need to stop the stupid thing of changing clocks. Humans have circadian rhythms. We're good having rhythms like cats. You know, we like things to happen at particular times of the day, and changing daylight to daylight saving time messes that up. I'm going to spend the next 4 or 5 days having messed up sleep pattern because of this. Anyway, yes, and what are we doing with all this time that we save? Are we hiding it under the mattress? Are we putting it in a high savings bank account? I feel like we've saved enough daylight by now. How about we start saving nighttime instead? Anyway, no science. There's no scientific basis to daylight saving time. We should abolish the whole thing. Stop doing it. Stop changing our clocks. It makes no sense. Yes, this is the rant that happens every 6 months. And I once again had to figure out how to change the clock on my oven, which requires kind of a PhD just to figure out how to change the bloody clock on the bloody thing. Anyway, my oven time is correct now. Coffee machine is easy. You just unplug it, plug it back in, and it asks you for the time. Much easier than trying to figure out the actual change time button. Anyway, already got that rant out of the way. Yeah, I need to do a recap of what you missed in the season finale of Cup of Cosmology. But that would imply a season finale, and yeah, we don't normally do that. I could start ending on cliffhangers like tune in next week to hear the answer, but that's a bit too clickbaity for me. What we do with the hour we save is we give it back a few months later. Yes, like a hamster in an endless wheel. And then, if there's no net gain, what's the point? We makes no sense. Take up studying Lepidoptera, and then you always have permanently disrupted sleep patterns. Yes, that's why I chose to study physics, because that's something that doesn't disrupt my sleep patterns too much. Does keep me up at night thinking about weird stuff, but doesn't disrupt my overall routines too much, and that is nice. Routines are there for a reason; they should not be disrupted. Anyway, that rant is out of the way, so now we can get on with the actual cosmology and science. I do actually have a topic prepared today, but as always, these streams tend to be rather chaotic. So, yes, if I start leaving on a cliffhanger, I'll need to start each episode with a recap. Last week on Cup of Cosmology, yeah. Then I feel like this would derail the whole structure of the show. Could be interesting. Maybe at some point I start doing this. Whenever we do quirks and creativity and general relativity part 2, we'll do a brief recap of part 1, and then we can pretend that's a to be continued episode. Okay, so there is actually a topic today, but as always, any questions on topic or off topic are always welcome. I'm always happy to go down random tangents and take the stream in random directions. So happy to do that as well. But there is a topic I want to get to, but we already have a question from James about black holes. If you were rotating around a black hole, would time be different? My response to this question is the usual, with respect to whom, because time is relative. You will always experience time as passing at 1 second per second. You will always experience time as advancing normally. But if someone else is watching you rotate around a black hole, then someone else would see your clocks ticking slightly differently to their own clocks, mainly due to your proximity to the black hole and then due to the rotation itself. But unless you're rotating close to the speed of light, the motion itself around the black hole doesn't have much to do with the time dilation, but getting close to the black hole does. And because black holes are big, weird gravitational objects that are kind of warping and dragging space-time, they are also, they're warping space-time, which means they are also going to have some time dilation effects because of the big, massive rotating object. But the biggest effect you'll notice in terms of time dilation is being close to the big, massive object. However, again, this is not something that you yourself would notice as far as you're concerned. Your clocks are still ticking at 1 second per second. It's only other people trying to measure time on your clock that would see it passing differently to their own clocks. This is a standard thing with time dilation, that you always need to ask a question of with respect to whom. Okay, so main thing I want to talk about today is the first elements in the universe, the elements that were formed 3 minutes after the end of inflation or after the Big Bang, depends on how you like to define the early universe. The reason for this is a couple months ago, 2 months ago, I gave a talk for the iTelescope network where I talked about the first 3 minutes of the universe. This video is now on YouTube. It was really fun. And if you don't know the iTelescope network, there's pretty much a seminar a week now, and it's always people in science giving general public talks, and a lot of them are really cool. I've done 3 for the iTelescope network by now. The links are on YouTube as well. So yeah, when I gave this talk, the topic was the first 3 minutes, and it included a discussion of something known as the lithium problem. And then I was talking with my colleagues, and a lot of people were like, I don't think I'm familiar with the lithium problem. So I promised the students at my university that I would, or the students in my group, that I would give a talk to them on the lithium problem, and this happened on Friday, which means the lithium problem is in my mind. So today I want to tell you all about the lithium problem. But before I jump into the lithium problem, I'm going to recap first 3 minutes after the end of inflation. So we're going to build up something known as the lithium problem and potential solutions, but there's some other things we need to get through first. So of course, I need to bring up my trusty image here of the evolution of the universe, which is this one here, also known as the cosmic condom. Why does it take hours to explain the first 3 minutes of the universe? Because a lot of stuff happened in the first 3 minutes of the universe. Forces were separating, things were stabilizing, particles were annihilating with antiparticles. There was a lot of stuff going on in the first 3 minutes of the universe. Okay, so we have this picture here, our standard map of the evolution, our standard cartoon depiction of the evolution of the universe. On the far left here, you can see the Big Bang, which technically should not be before inflation, but anyway, Big Bang, beginning of everything. as far as we know. Then we have this period of inflation where the universe expanded exponentially. Technically, we all start our clocks after the end of inflation. Yes, I'm sorry. I'm sorry for the unofficial name of this plot. It came up once in the stream, and now I can't unsee it. So now this image officially has an inappropriate name. Sorry about that. I pass this on to everyone now. So inflation, universe grows exponentially. Thing about inflation is we don't know how long it lasted. Inflation could have lasted billions of years, which means we actually start our clocks at the end of inflation. And given that we say that the Big Bang is time equals zero, then technically the Big Bang is after the end of inflation. This is a semantic question that depends who you ask. But Big Bang, inflation, we start our clocks at the end of inflation. Then the first particles are going to form, and then a bunch of stuff is going to happen, and you're going to speed up to the CMB, the cosmic microwave background radiation, this thing that happens 380,000 years after the end of inflation. Hey, Savant, great to see you here as well. I saw a cool graph of table of elements. Yeah, maybe that's the same one I'm going to show at some point today as well. Okay, so what I want to talk about today is everything that happened from the end of inflation up until the time of the cosmic microwave background radiation. Actually, I'm not going up to the CMB. I'm going to stop 3 minutes after the Big Bang, but I just mentioned CMB, so, perfect chance to throw this at you. It had already been 12 minutes, so it was overdue. Do we know if the universe inflation expanded as a perfect sphere or some other shape? That's a cool question. So we don't really know. So inflation would have driven the universe to be flat. We know that today the universe is flat. This might seem weird because we're talking about a flat thing that is 4-dimensional, 3 space dimensions, 1 time dimension. So the universe is flat today. We don't know what shape it had before inflation, but inflation would have naturally driven the universe to be flat. In fact, one of the biggest motivations for inflation is to solve the question of why the universe looks inexplicably flat today. Inflation would naturally push everything to be flat. So you can imagine if you're on a balloon, and as this balloon, imagine you have an ant walking on a balloon, and this balloon inflates and inflates and inflates and inflates. At some point for the ant, it will look like it's walking on a flat surface because it would be so blown up that it can't see the curvature. So when we're talking about the universe, the shape is quite unclear. At the end of inflation, we know that it was pushed to be flat. And there's a great question by Scotty of how can it have a shape if it is everything? And this is a great question because when we're talking about shapes, we usually imagine there's kind of a boundary, an edge to the shape. But the universe is everything in existence. There can't be a boundary, there can't be an edge of it. So your brother thinks the Earth is flat. Well, I'm sorry to hear that. There's plenty of evidence out there saying the contrary, but some people are stuck in their ideas and it's very hard to change their mind. You like the cool table of elements that shows how when things were created? We will get to that as well. Okay, so talking about the shape of the universe. So we know that the universe is homogeneous and isotropic. This means it looks the same in every direction from wherever you look. Whichever direction you look in the night sky, everything appears to be more or less the same. And of course, this doesn't mean things are exactly the same because obviously looking at the moon is very different to looking at a galaxy. So what we mean when we say the universe looks the same in every direction from wherever we measure is that if you take a step back and look on large enough scales, everything appears to be very, 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 very similar. It doesn't matter if you pick this galaxy or that galaxy, everything really looks the same. So this basically tells us that there is no privileged position in the universe, that from wherever you look, everything should look the same, our region is not special. So the universe should be homogeneous, which means the same in every direction, and homogeneous and isotropic. Isotropic meaning the same in every direction, homogeneous meaning the same in every direction, regardless of when you look at. Once you've assumed that the universe is homogeneous and isotropic, there are only 3 possible shapes you can have. The universe could be curved, the universe could be kind of a saddle like a Pringle crisp, or the universe could be flat. Now here we can go back to Einstein's general relativity. Einstein's general relativity tells us that space-time is bent by the presence of energy and matter. So matter in the universe bends space-time. The bending of space-time tells things how to move. Now, with this means that we can take all of the matter content of the universe and see what the overall geometry of the universe should be. If the universe has exactly the right matter content. It could be flat. If it has more, it could be curved. If it has less, it could be this hyperbolic shape. So we know that today, out of these three things that you can see here, we live in the bottom case. Basically, if you go anywhere in the universe and you draw a triangle, the angles add up to 180 degrees. This is a very mathematical description. However, before inflation, it could have been any of these three. Yes, please do go grab Pringles to entertain, because now that I've mentioned Pringles, or you could grab a chocolate ball as well, because there's a ball on the screen. You can go grab any type of food here. So we know that today we're in the third option here. The universe looks flat. However, before inflation, it could have been any of these three or something else entirely, probably one of these three. And inflation would have naturally driven it to be the bottom one here. What's in the Z direction? Yes, good question. This is just a visualization here. Now we're trying to visualize a 4-dimensional surface, or even a 3-dimensional space onto a 2-dimensional projection. It's not going to work. So it's very difficult to visualize this because the universe does have 3 space dimensions, 1 time dimension. So anytime we try to think about what it means to be flat, yes, and what are you drawing these triangles on? You draw the triangles on the fabric of space-time itself. So the triangles can be a bit confusing. So another way to think of this is, imagine you take a football and you go anywhere in the universe, far, far, far away from any gravitational objects, so far away from stars and planets and black holes and clumpy dark matter, and you put your ball down. You just put your ball somewhere in the universe. Now, in a flat universe, this ball is going to stay still. However, if you have any type of curvature, this ball is going to be accelerated, kind of like putting a ball on a hill. So if there was any type of intrinsic curvature to the universe, you would see a very small motion if you put an object at rest in the universe. Now, of course, it's very hard to put an object at rest and see what happens, but this is perhaps a slightly easier way to visualize it than thinking of the triangles. But yes, we know that today the universe is flat. We don't know what the universe looked like before inflation. Inflation deletes the memory of anything that came beforehand. This means that it could have been spherical beforehand, it might not have been, but we know that today the universe is flat. But it is an excellent question to ask what the shape of the universe was before and even during inflation, and the short answer is we don't know, but we know what it is today. And that is indeed one of the motivations for inflation. Okay, I think I caught all of the questions there. So, early universe, what happens? Inflation happens. At the end of inflation, particles start forming. You get a lot of particles, you get a lot of antiparticles. For some reason, we had a bit more particles than antiparticles, a bit more matter than antimatter, which was great. Because at some point, as the universe cools down, particles and antiparticles annihilate. They produce a bath of radiation, of photons, particles of light. If there had been equal parts of matter and antimatter, everything would be gone today. We wouldn't be here having this conversation. For some bizarre reason that we don't know, there was a bit more matter than antimatter, and this bit more matter means that we're here today asking why there was more matter than antimatter. Also, in the first few seconds, or the first few picoseconds, a fraction of a second after the end of inflation, the force is separated. We know that there are 4 forces that govern the universe: electromagnetic, responsible for electricity and magnetism; gravity, responsible for things staying in orbit and objects falling down and curving space-time; strong force glues everything together; and weak force, radioactive decay, and other similar things. In the early universe, we know for sure that the electromagnetic force and the weak force were combined together in the electroweak force. We think if you go back further in time, and therefore to higher energies, the strong force might have been combined with them. This is what would be known as a theory of everything. A grand unified theory. And if you go back even further in time, maybe gravity was added to the mix. This would be the theory of everything, but for this we need quantum gravity. So early universe, inflation happens. We don't know how long that lasted. Forces begin to separate. Particles annihilate with antiparticles. You go from having a hot quark glue on plasma, where all of the quarks that make up particles later on are just in this big soup. And at some point, these come together and start forming the first protons and neutrons. So within the standard model of particle physics, the basic building blocks, you have different types of quarks. You have 6 different types: up, down, top, bottom, strange, charm. And these can't live alone. So in the early universe, they were in this big soup. And at some point, they went from being in the soup, the strong force became more efficient, so they could bind together, and then you would take like 2 ups and a down to form a proton, or 2 downs and an up to form neutrons. So you go from having this hot quark gluon plasma soup about 10 seconds after the end of inflation to having actual protons and neutrons. Electrons are there as well, doing their own thing. Dark matter's broke away, doing its own thing by now. But you do have now a soup of protons, neutrons, electrons are around there, photons, lots of particles of light. So you have all of that around there as well. What happened to truth and beauty? We renamed them top and bottom. So there was some debate initially, the 6 quarks. Some people used to say, okay, up, down, truth, beauty, charm, and strange. And then at some point it was changed to up, down, top, bottom, charm, and strange. So if you've heard of truth and beauty, it's the old names for top and bottom. But we all like tops and bottoms a bit more than truth and beauty. Okay, do we know exactly when all the antimatter disappeared? Was it before or after the universe could support elements? Beforehand. So strangeness is just strange quark now. So matter and antimatter can annihilate as soon as this process becomes energetically efficient, which is in the first fraction of a second after the end of inflation. So by the time we get to the stage where protons and neutrons can start binding together to form elements, which is exactly what we're going to discuss soon, by then most of the matter and antimatter has annihilated. You can still produce new antimatter, like we know we can produce antimatter today in different ways in the universe. But in the early universes, annihilation happens before the first elements begin to form. So you don't actually form you don't form antiprotons and antineutrons before then. All of these have already annihilated. They annihilate very, very early on in the universe. So particles, antiparticles have annihilated, forces have turned on, you form protons, you form neutrons. Antimatter is no longer a thing you have to care about. And we would also prefer sub and bottom over charm and strange, just saying yes. But at that point, it's going to get a bit weird, I think, because you already have top and bottom. So yeah, they're badly named anyway, because we're physicists and everything is badly named. We're just terrible at naming things in general. Realize my tea might actually be drinkable. Have no idea why somebody thought a strawberry and cream rooibos tea was a good idea, but apparently it actually is, and this somehow works. I bought a box of 20 random tea flavors. It's like adventure time with tea. And you get some really good things, and then you get rooibos or redbush with strawberry and cream. Interesting tea. Anyway, I'm ignoring the comments that are coming in because yes, I see people did pick up on my top and bottom reference there. So anyway, particles, early universe, tea is now drinkable. Exactly, tea has reached optimum points. You know, complete tangent here, but YouTube does a thing where it automatically adds chapters to my videos, and I could go back and edit them, and I don't. So if any time you're watching any of the old streams on YouTube and you go to the chapters, you'll see that it's added chapters. And the way it does this, I don't want to know how it does it, but it picks out key phrases or key words and assigns them as titles to the chapters. And this means that sometimes looking back, because I have a tendency to go on tangents like this one here, the YouTube chapters end up having really weird names. And there was one stream from some months ago that one of the chapters is called Cucumber Tea is a Quantum Singularity. So obviously when I saw that, I had to go watch it, and I did indeed say that exact phrase. So I'm now doing this to see if YouTube is going to add a chapter on YouTube chapters, because I'm really amused at some of the random names it pulls out. Anyway, someday it's going to pull up one of my really weird offhand comment jokes and put that as a chapter title, and then I'm going to have to go in and change it. Close that tangent. That was a digression there. Okay, about 10 seconds to 3 minutes after the end of inflation, antimatter is mostly gone. We have a lot of protons, we have neutrons, we have electrons around, we have photons, lots of particles of light. And now we reach the point where it becomes energetically efficient for protons and neutrons to come together. And this is when we're going to start forming the first elements. So what we're going to do here is we're going to have a fusion process. And this, you might remember that fusion, if you've heard much about fusion, it's when things come together. This is what happens at the center of stars. This is how stars get their energy. Stars start out being a lot of hydrogen and maybe a small amount of helium. And this just burns and burns and burns and gradually produces heavier and heavier and heavier elements until at some point you have things like carbon and oxygen and iron. And then a star explodes as a supernova and pushes. That is a great title for your first cosmology book. I'm not sure what you're referring to, but I'm hoping it's T is a quantum singularity. Cucumber T is a quantum singularity, because that would be a very funny title for a cosmology book. Like, definitely you have to read that to figure out what's happening. Just hoping blue dwarfs made it into the chapter name Hall of Fame. I do not think so, actually. I will check. There's one video specifically that might have blue dwarfs in the chapters. I will check. Okay, so we know that fusion happens inside stars. You go from hydrogen, helium, you gradually build the heavier and heavier elements going through carbon and oxygen and nitrogen and iron, stops at iron. And then when a star explodes as a supernova, it scatters these elements throughout the universe. This leads to Carl Sagan's famous phrase, if you are stardust, because all of the carbon in your body, all of the oxygen in your body was formed in a star that was reaching the end of its lifetime and then exploded throughout the universe, which is very, very cool. But where did the hydrogen and helium in these stars come from? For that, we need Big Bang nucleosynthesis. So Big Bang nucleosynthesis is the fancy name for early universe fusion of elements. I'm not sure which is a better name. Big Bang nucleosynthesis is kind of technical, but and it's not even during the Big Bang. It's like 3 minutes after the end of inflation. But anyway, 3 minutes after the end of inflation, approximately, is when we reach the right energy conditions for fusion to start in the universe. So there are several different reactions that are going to take place, and we don't just stop at hydrogen and helium. So I am going to show you a diagram now of the different processes that can happen. So we're going to talk a lot about chemical reactions here, nuclear reactions. So, if protons and neutrons come together, you can gradually build up elements with heavier proton count and heavier neutron counts. Protons and neutrons normally exist in similar quantities in elements, but not necessarily. You can have some with a bit more, some with a bit less. But in the very early universe, about 3 minutes after the end of inflation, the conditions are met to form a series of chemical reactions, or nuclear reactions, that are going to trigger the formation of elements. We're going to form hydrogen. We're going to form deuterium, which is hydrogen with 2 protons. So a proton by itself is basically hydrogen. Now, I want to preface here that we do not have electrons invited to the game right now. So we're just forming the nucleus of the atom. We're not actually forming atoms themselves, because electrons will not appear. Well, electrons are there, but they're not going to bind just yet. Electrons will bind later on. So for now, what you're doing is you're just getting the protons and the neutrons and you're bringing them together. The amount of protons and the amount of neutrons is already set in the early universe. This is set by the strong force turning on properly and pulling out these quarks from the quark gluon plasma soup. So the relative abundance of protons to neutrons is already set in the early universe. So this is something that we can use as a starting point. And from here, we're going to bring the protons and neutrons together in different ways to produce heavier and heavier elements. Hydrogen, helium, deuterium, which is hydrogen with 2 protons, tritium, which is hydrogen with 3 protons. Then we're going to have a difference between helium-3 and helium-4, which again will be related to the amount of neutrons that it has instead of protons this time. And we're also going to form small amounts of beryllium and small amounts of lithium. Did the universe also have a lot of muon, tauon, top, bottom hadrons or baryon elements at this point? So there are 6 types of quarks, of course, and I've only mentioned mainly top and bottom. Sorry you have to go, David. As always, the replay will be up on YouTube, so whatever you missed, you can just catch in the replay. And I'm sure you know this by now anyway, but you can always catch the replay, and thank you for dropping by. So the reason we mainly talk about ups and downs and not the other ones so much is because ups and downs are the most stable ones. They're the ones that are less energetic. They have a bit less mass than the other quarks, and they're the most stable ones. So most of the time when we're putting things together, it's going to be using ups and downs and not top-bottom strange quark. Beryllium was very important in the Galaxy Quest movie. Yes, it was indeed. Tritium is how you take a miniature star. It's how you make a miniature star on Earth, according to Dr. Octopus. Yeah, I wouldn't quote Dr. Octopus as a reliable scientific source, but I do appreciate the sci-fi and fantasy references here. Okay, so chain reactions. This is what we're going to do. Okay, this figure might seem like a lot, so let's break it down. What you have here, going from left to right, you increase the number of neutrons. Going from bottom to top, you increase the number of protons. So if you find every arrow indicates a possible nuclear reaction. So if you find the N at the bottom of the screen, this is the neutron. From the neutron, you can have a decay neutron into proton, which goes to up one to the left. So it loses a neutron, it gains a proton, so it moves up and left. Okay, now you see that every arrow has something in brackets written above it. This is the reaction. The first thing inside the bracket is what goes in. The second one is what comes out. So for an example, if you take the P, the proton, and you follow the arrow to the D, the deuterium, which is hydrogen with 2 protons, you see it's got N, gamma, which is a photon. So what this is telling you is you take the proton, which is in the box, you take the neutron in the brackets, and what you get out is deuterium and a photon. And this is true for all of the other ones that you see here. To go from D deuterium to T tritium, you take 2 deuterium atoms, you smash them together, you end up with tritium and a spare proton. To go from deuterium to helium-3, which is helium with only 3 groups at the center instead of 4. So it has 2 neutrons and 1 proton, 2 neutrons, yes, and helium-4 has 2 of each. So you can see to go from deuterium to 3 or helium-3, you have 2 possibilities. You either smash 2 deuteriums together and you get neutron and helium-3 out, or you smash deuterium and a proton together and you get helium-3 and a photon out. Did you answer my question? I gave a hand-wavy answer that ups and downs are the most stable and the ones with the least mass of all of the quarks. So these usually break down into ups and downs. So most of the time when we're talking about any type of baryons that are formed, they're made up of ups and downs. You can do things with strange and quarks, but they're a bit short-lived. The same is true for muons. These usually decay or interact via the weak force and change slightly. So it's always the kind of lightest of the particles that we talk about. So that's why we're talking about ups and downs. But this was a hand-wavy question because the actual answer would involve bringing up a lot of particle physics that is hidden somewhere in the base of my brain. So yeah, as Paul is saying here, the more things you have, the more things you can make. Once you have several different building blocks, you can put them together in several different ways. But the one that we're interested in today is lithium. You can see lithium, all of these are interesting, but I specifically want to point out lithium. So you see lithium is the rightmost one, 7 lithium, and there are actually 2 ways we can get to lithium. So we have the direct route, where you have tritium and helium-4, you smash these together and you get lithium and a photon coming out. And then you have the indirect route, where first you form beryllium. You can do this by smashing together helium-3 and helium-4. You form beryllium, and beryllium can then decay into lithium-7. So you have the direct route producing lithium, which is from tritium to lithium, and you have the indirect one, which is via beryllium. So you have these 2 different ones. You can either go beryllium-lithium or directly to lithium. But then you'll notice there's also an arrow from lithium down to helium-4. This means that lithium can actually decay into helium-4, which if you want lots of lithium is problematic because it can actually go backwards. So is there a distribution between these early elements and isotopes? That is an excellent question. The answer is going to be yes, and it's going to depend on what is the most energetically efficient. So some of these reactions here are more likely than others just because they're more energetically favored. This depends on how well protons and neutrons bind together. So some of these are going to be favored. Some of these are going to be much more relevant. And this is going to be an important point. James is saying, are all of these reactions only relevant to early universe energy, or can these be done in colliders today? These reactions also take place in stars. This is just a starting point of any nucleosynthesis process, of any fusion type process. In the early universe, you only had the right energy for long enough that you could go up to lithium, you couldn't go further. But in the center of a star, you start with this process and you carry on doing it and doing it. And you go through the same chain, you just then expand it all the way up to iron. So this becomes a lot bigger. But this is the starting point. Now, in order to do these efficiently in a collider, we would need nuclear fusion, and that's very, very, very difficult, but we are working on that. So the amount of each element that would be produced, the distribution between these different things, depends on how favored these reactions are. And for an example, the reaction to go between helium and beryllium is more energetically efficient than the one to go between tritium and lithium. Likewise, between tritium and helium-4, this is much more dominant than between tritium to lithium. So this is good because this means we can calculate this. Based on what we know of the strong force, we can figure out the amount of protons and neutrons that we had to start with. But there is one thing we don't know. You'll notice that a lot of these reactions have photons involved. And there's one thing we don't know about the early universe, so that we can't calculate just based on principles. We would actually have to measure is the ratio between baryons and photons. So how many baryons or how many protons there are versus how many photons there are. And this is going to be an important number. Now, the cool thing is this is something we can measure using the cosmic microwave background radiation, the oldest light in the universe. So you can use my friend the CMB to measure the ratio between baryons and photons. And this is good because if you start with this image, this diagram here, you can calculate how much of each element we should produce. Just based on this, there's going to be some uncertainty attached, like which is most likely. There's always some chance here, whether you do one decay channel or another. But you can say like 70% of the time, approximately, we do one of these, 30% of the time we do another, which means just based on this diagram and what we know of how the strong force worked before this became a thing, before Big Bang nucleosynthesis, we can calculate how much of these elements should have been formed in the early universe. All of this will depend on one number, which is going to be the ratio between baryons and photons. This means that you do all of this, but you leave one number unknown. And then you measure this number and you plug it in, and then you can predict the exact amount of these elements that should have been formed in the early universe. We know that helium would have been formed in a lot higher quantities than beryllium and lithium. And because lithium can decay into helium, there's not going to be much lithium. So you're going to have a lot of hydrogen, you're going to have a lot of helium, and you're going to have a very small fraction of beryllium and an even smaller fraction of lithium. But this is something we can calculate. This is something that we can already put in. We know that after this process were done, for every 4 particles that you picked up, statistically 3 of them were going to be hydrogen, 1 was going to be helium. About 25% of it was going to be helium, 75% was going to be hydrogen, and less than 0.5% was going to be beryllium and lithium combined. So this is really important because, okay, before I get to why this is important, cliffhanger, at high energy regimes, do we also implicitly assume the strong nuclear force acts the same way at lower regimes and electroweak is not separated here? By this point, all of the forces have separated. So we are at high energies, but not too high where the forces could unite. So this is after electroweak phase transition. So the electromagnetic and the weak forces have separated. We're assuming that the strong QCD phase transition has happened. So this means that we've gone from having the strong force keeping everything as a quark gluon plasma to the strong force allowing the formation of protons and neutrons. So by now we are still at high energies, but not enough where we expect the strong force to behave any differently to what it does today. Hope that answers your question. And I know I just threw out words like phase transition, but based on the way the question was asked, I think that will answer your question. If not, please ask again and we can go through that again. Okay, so why is this important? This is important because this is a prediction from the Big Bang cosmology. So Big Bang is our theory of the evolution of the universe starting from the end of inflation until today. And this is a prediction. If everything we've understood about Big Bang is correct, we can predict the amount of these elements that are formed. We can predict how much hydrogen, helium, lithium, beryllium, deuterium was formed in the early universe. We just need one number, which is going to be the ratio of photons to baryons. But this is a prediction we can make, which means this is something we can test for Big Bang cosmology. But of course, how do we measure the elements that were formed, 13.82 billion years ago? And the answer to that is we need to find really, 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 really young galaxies. So galaxies that were formed ages ago but haven't yet kind of evolved. So what we want to do is we want to look for really distant galaxies. The further into the night sky we're looking, the further back in time we're looking. Which means if you look far enough away, you can find galaxies that are still very much in their infancy. Why do we want this? Well, because if galaxies are still very much in their infancy, the stars in there haven't had enough time to produce these heavier elements. We know that if you go to any galaxy here, the sun is producing these heavier elements. Every star is producing these heavier elements. So then if you wanted to measure the amount of lithium in the universe, in the solar system or in the Milky Way, it would be very hard because there's lithium kind of everywhere from other stars that have exploded a supernova and spread out the lithium that was formed in the stars. So you need to separate the elements formed in a star from the elements formed in the early universe. So to do this, you need to find a place where stars haven't had time to form these elements. So you can use either very, very, very distant galaxies or very young galaxies, or things like dwarf galaxies where there's not many stars, and you can kind of account, like based on the stars we see, we expect that stars are contributing this amount to the lithium, to beryllium, to deuterium. Everything else is a primordial fraction. So we have a prediction from Big Bang cosmology, and we have a way of measuring it. We look for these things around us, look for these very, 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 very far away galaxies, and then we measure the composition of the space in between stars, the space in between stuff, where there's just the trace elements of residue of these early universe Big Bang nucleosynthesis. And of course, just want to make a comment here that I mentioned at some point that electrons weren't invited to this party. The electrons do come in later on. So around 380,000 years after the Big Bang, as the universe cools down, the electrons can actually bind together with these primordial elements. This happens when we produce the CMB. At the time at which we produce the cosmic microwave background radiation, fourth time today, spoiling you all. This happens when the electrons combine together with the hydrogen, with the helium in the early universe, with the lithium. The electrons combine together so the photons can no longer bump into them, and then they break away and start traveling freely. So there's this two-step process. You have the recombination of the electrons combining with the nuclide to form actual atoms, and then the CMB breaking away and traveling to us today. So in the early universe, you form these trace elements. These trace elements are a prediction of Big Bang cosmology. And of course, what we want to do is measure them. To do that, we can go to very distant galaxies where stars have not had much time to murky the waters a bit. We're still quite primordial. We can measure the elements there and then see how they compare. But again, there is one number that we are missing, which is the ratio between photons and baryons. This is going to set the starting point for our reactions. So the JWST finding super early galaxies would change our assumptions of element distribution. It wouldn't, it would change the measurements, but as I'm about to show you, we already have very, very, very good measurements of these things. So JWST will help us, but not substantially, because this is something that is already very well measured. So I'm going to show you the results of these distributions, and it's going to be a scientific figure with a lot to take in, so we're going to break it down. You see three different plots here. The top one is basically the amount of helium-4 in the universe. The second one, the one we're going to care about, is deuterium, and the bottom one is going to be lithium. The top one, we're talking about mass fraction, so how much of the universe was in the form of helium versus hydrogen. The second one and the third one is going to be a percentage, so it's very, very similar quantities. Okay, on the horizontal axis, we have two different things, one on the top, one on the bottom. They're the same thing, just expressed differently. This is going to be the ratio between photons and baryons in the early universe, which we can also express as the density of baryons. So on the top horizontal axis, we're expressing it in terms of the amount of baryons in the universe. In the bottom axis, we're using the ratio of baryons to photons. Okay, first thing to notice here, we have this vertical gray bar that is labeled CMB. This is the ratio between baryons and photons in the early universe. For every 10 billion photons, we had one baryon. There were a lot of photons in the early universe. For every 10 billion photons, you had one baryon. But with this measurement, you can set the starting point for all of your chain of reactions. And with this, you can actually make the predictions done properly. Okay, the predictions for the different elements are shown in the colors. You can see the top line, we have this blue one denoted helium-4. This is the prediction for how much helium-4 there should be in the universe. In the second one, we're going to focus on the red line. This is deuterium. You can see that it's a very nice red line here. And in the bottom one, we have lithium, this nice orange line here. Okay, so these are the predictions from Big Bang cosmology. The vertical line is what we have measured from the CMB. So that tells us where we should find our predictions. So now we do the measurements. We find these really, really distant galaxies, these primordial galaxies, and we measure the trace amount of elements there. And this is going to be the horizontal gray bands. So we focus on the top one, helium-4, CMB coming one way, helium coming another, and you'll see the measurements that we have from galaxies in horizontal goes right over them. I circled it with a green circle here, and you can see there is perfect overlap. This is incredible. This means that we were able to predict exactly how much helium there should be in the universe based on our understanding of Big Bang cosmology, and we found exactly the right number. The lithium band is thicker because there's more statistical fluctuation because there's several channels to get to lithium, and then there's a decay probability of lithium decaying into helium, because you have that added decay channel. It changes like how much of it has actually decayed when it decays with a certain probability. So that means that the lithium prediction is going to have a bit of a bigger uncertainty to it. So the lithium one is going to be thicker than the other ones. Okay, second one again, we're just focusing on the red line. We're not focusing on helium-3, we're focusing on deuterium. Again, you can see the horizontal bands here, the gray bands, the vertical band from the CMB and the prediction all align perfectly. I circled them in green. Again, the amount of deuterium we measured was exactly what we predicted. This is a massive success for the Big Bang cosmology. Right? Big Bang cosmology predicted that we should find a specific amount of helium and a specific amount of deuterium. And we measured exactly that amount. This is an amazing success, and this is considered one of the biggest pieces of evidence in favor of Big Bang cosmology. Wouldn't such early first-generation stars be mostly type O and live for only 100,000 years or so before they go supernova in partial galaxies? I'm not sure. I'm not an expert on star formation, but I know you're interested in metal-poor stars here. So you want population 2 stars that are metal-poor. And these you can find in primordial galaxies, but you can also find other types of galaxies that have very metal-poor stars. So I'm not completely sure on how long the stars would live. I'm not too familiar with stellar evolution stages, but you just need to find stars that are metal poor. This can be done in very distant galaxies or in dwarf galaxies, but there are other environments where you can also find these metal poor stars. Hope that answers your question. So helium-4, perfect match. Deuterium, perfect match. Success. These are the ones that we predicted. I don't show it on the plot, but helium-3 is also perfectly exactly where it should be. So 3 out of 4 are perfect. But now comes the fourth one. And given that I've made several comments about the lithium problem, you can see where I'm going with this. So let's look at lithium. Lithium, again, vertical band from CMB in grey. Horizontal band is what we measure, also in grey. And the orange band is the prediction. And now you see that I circled it in red because where the prediction is not where the observation is. So the grey horizontal band is where things should meet, and instead they meet slightly above. So you see we're off slightly. It's not substantial, but it's a factor around 3. This means that we're measuring 3 times less lithium than we should. And 3 is not a lot, right? It's still approximately right. It's the right order of magnitude, but it's a factor 3. So we would expect this whole horizontal band to be lifted up to lie on where I put the red circle, and instead it's not. So we're observing 3 times less lithium than we should in these primordial spaces. Now, this is what is known as the lithium problem in cosmology. And it's very, very, very difficult to explain because helium is perfect. Both isotopes, helium-3, helium-4, are perfect. Deuterium is perfect. So what went wrong with the lithium prediction or observation, and should we be concerned? The general impression is we should not be too concerned about this because there's a lot of things that could maybe explain it, we just haven't found any yet. But given that 3 out of 4 of these Big Bang nucleosynthesis predictions were perfect, the last one, it looks like way more of a difference in the thickness of the bars. Yes, so this is, if you want it in statistical terms, this is about 2.5 sigma off of where it should be. So the bands give you the overall measurement, they are 1 sigma. So if you take the grey band and you consider 2 sigma would be increasing it very slightly, you're almost there. So it's about 2.5 sigma away, or a factor 3. This is very interesting, and it's something that has baffled scientists for years. Why does the lithium curve have a knee-bent shape? Excellent question. It's because lithium had 2 possible channels of production and a decay channel. And this means depending on how many photons you have, so the thing you're moving left and right, the ratio of baryons to photons, different channels are more energetically favored. If you have if you increase the baryon to photon ratio, you go to a different chain. If you decrease it, you go to another chain, and the decays happen kind of in the middle. So you have the amount that you're producing depends strictly on the amount of photons you're adding because of the different decay channels. Because the helium-4 and the deuterium don't really have decay channels, you don't see that. But because with the lithium-7, you have 2 different production methods and a decay channel, you end up with a shape that is going to change dramatically. That is the reason for that. It's something that is exactly how we predict it to be. So how can we solve this? There are 3 types of solutions. Any solution people come up with fall into these 3 categories. Option number 1, we say there's something wrong with the measurement of lithium. So we say it's an astrophysics problem. Now, there could be a lot of things happening here, like maybe we haven't accounted for how stars behave properly. Maybe when we say, okay, we know how much lithium is produced in stars, maybe we're wrong, maybe we're off. There could be something on the outer layers of stars where there's a lithium capture phenomena, where lithium is captured inside the stars, and therefore you measure less of it. This is actually one of the proposed solutions, that lithium is captured by stars, and this reduces the amount that you're going to observe. So the type of solution 1 is to say the measurement is wrong. So what you're saying here is the horizontal grey band is wrong. Number 2, you say that our prediction is wrong. Maybe there's something that we didn't take into account in this whole chain of reactions. For an example, there could be some quantum tunneling processes where particles tunnel from one energy state to another, which could make our predictions for which chain is more likely change. And that would shift the whole orange thing up or down. So here we're saying that the orange curve is wrong. Solution 1, astrophysics. There's something wrong with the measurement of the lithium. Option 2, there's something wrong with the nuclear physics. So we didn't understand, or there's something we're missing about how lithium is formed, so our prediction is off. And then there's option 3, which in my opinion is the most fun one, which is to say, okay, maybe something happened between Big Bang nucleosynthesis and the time of the CMB, which means that the vertical CMB line should move. The problem here is you need it to move only for lithium and not for the other ones, and this is ridiculously difficult to achieve. There are some things that could maybe do this. For an example, if you have decaying dark matter, so dark matter in the early universe that decays in a specific way, it could affect how lithium then, how you do this whole chemical nuclear reaction and then affect how much of each thing you're producing. You'd basically be changing the ratio of photons to baryons once this process has already started. So then you have the interplay where you have this dark matter decaying and adding more photons at the right time. This was one proposal. It doesn't work. It doesn't solve the problem. But this third category is basically saying new physics. Another option was supersymmetry, which is something that a lot of string theorists were interested in. It's a way where you say that every particle has a symmetrical particle, kind of a partner. This is something that we were hoping to find at colliders and we haven't found yet. So supersymmetry is kind of on the ropes, depending who you ask. So this doesn't appear to work either. So this is a problem. This was a prediction from Big Bang cosmology and it's wrong, but it's only wrong by a bit, right? Helium-3 is fine, helium-4 is fine, deuterium is fine. Not only fine, these three are perfect. And then lithium is off by a factor 3. Should we care? The general consensus is no, we should probably don't need to care because, it's a minor inconvenience. It's not dramatic. You can solve it by either saying the predictions are wrong, the astrophysics is wrong, or new physics. Unfortunately, we haven't found a completely satisfying solution that can fully resolve the problem. So that's cool. I think this is a very cool and often overlooked thing that we have this issue within the Big Bang cosmology. The problem is everything else in Big Bang cosmology is so incredibly good that it's very, very difficult to find a way to solve this without messing up everything else. A lot of people have reached a conclusion like there's probably something going wrong with how we do the measurement. It's very difficult to measure the amount of lithium in stars. So there's probably something going wrong with this. But because we don't yet have a concrete answer, there's still a lot of room to play. So, as I said at the beginning of the stream, I gave this talk to a couple of students in our group on Friday. We have a very nice thing. We have a journal club where we don't allow any permanent members of staff to join. So it's like no professors allowed, and it's very informal and chill. And I presented this, and everyone was like, oh, this is interesting. And then we went and spoke to a professor about it, and the response was like, yeah, it's just astrophysics. Nobody cares. So there is this general opinion that a lot of people are like, meh, we'll probably figure it out. But it is one of the lingering problems with Big Bang cosmology. So could it be because of the different isotopes of lithium? Excellent question. And I should mention here that what I've presented is a very simplified version of all of this, because you also have lithium-6 at play as well as lithium-7. And there's different isotopes of lithium that you need to account for. This has been accounted for. It doesn't solve the problem. So I provided a kind of simplified version of the problem here, but it's a bit more extensive than what I've said. Sterile neutrinos interactions in lithium formation could be called for a dark matter candidate. Yes. Sterile neutrinos are a hypothetical dark matter candidate. I'm not sure if you can solve the lithium problem with sterile neutrinos. I think people have tried. And it would be cool if we find a solution. But yes, there are ways where you can blame dark matter. If in doubt, blame dark matter. Given that we haven't found dark matter yet, it is an easy place to put the blame because it can't defend itself yet. So this is cool. I'm not saying physics is broken. It's just an anomaly. It's a problem. It's compelling, right? It compels me. So it's something that is interesting. And it's not really hyped up enough because, okay, a factor 3, there's a lot of things that could go wrong. But it is very cool when you think about it, that, all of our predictions are really close. And this one is just very slightly off by a factor 3. So just a factor 3 off, no big deal, basically, yeah. I mean, if it was off by a lot more, by 1 order of magnitude, you're worried. But a factor 3, when there's so many steps involved in the calculation, okay. Fine. Wonder if you could get away with that at the bank. Like, it's just a factor 3 that I underpaid. It's fine. Physicist, order of magnitude. But it is interesting. It's not a crisis. It's not a problem. It's definitely not as dramatic as other problems we have in cosmology. But it is very interesting to think that this is something that we've known about for 20 years and we still haven't been able to solve. Of course, you could also say we've known about dark matter and dark energy for many years and also haven't been able to solve those yet. So lithium problem is a fun one to think about. So I thought that was a fun topic to talk about. Lithium problem is fun, and we get to review where the elements came from, because I focus on the lithium problem at the end, but there's also all of this cool thing about where the elements are coming from. Mercury orbit for Saturn was also only a small problem, but we got a new theory of gravity out of it. Yeah. I see two people mentioning this. Yeah, it's a small problem compared to everything else that works perfectly well. And because there's a lot we don't know on the astrophysics side, it's very easy to dismiss this problem. But it is still lingering around here. But apart from the lithium problem, another thing we've reviewed today is where the helium and hydrogen in the universe come from. And I think this is really cool. And there was the mention earlier of the very amazing periodic table of elements based on where things come from. And I want to show that at the end because it's really cool. So we know that all of the heavier elements, carbon, oxygen, all of these were made in exploding stars. Hydrogen and helium were made in the early universe. So if we consider periodic table of elements, here we have it color-coded by where elements were formed. You can see in dark blue, we have Big Bang fusion. And this is helium and hydrogen and helium at the top. Then in orange, we have things like merging neutron stars. In yellow, we have dying mass black stars. And if you look at lithium, there's this small, lithium is second from top on the left. And you can see there's this very small blue band from Big Bang fusion. We have cosmic rays coming together for some elements, and then we have exploding massive stars in green, exploding white dwarfs, dying low mass stars. And then on the right above me here, there's another image, which is the average composition of a human. So humans are mostly oxygen, carbon, and, mostly carbon, oxygen, trace amounts of nitrogen. And all of these were formed in dying stars or exploding stars. So this is where the phrase of "you are stardust" comes from. But if you look at the periodic table of elements, you'll see that hydrogen and most of helium are formed entirely in Big Bang. Big Bang fusion, so 3 minutes after the Big Bang. You can form trace amounts of helium later on, but most of the helium and all of the hydrogen come from this early time. 10% of us, 10% of every human on average is hydrogen. This means that 10% of your atoms were formed 13.82 billion years ago in the early universe, following this chain of reactions that I showed before. So yeah, we all stardust, but we are also all universe dust. 10% of your atoms are 13.82 billion years old. And when you're done with them, they're going to go out back to the universe and continue on their journey. And I think this is an absolutely amazing fact to know that, 10% of you is ancient and old and intrinsic to the universe and been there since 3 minutes after the end of inflation. Part of you has lived through most of the cosmos, almost all of the history of the cosmos. And when you're done, that part is going to go back to the universe. All of you is just going to go back. Your atoms are going to be reused. I find that's an amazing thing. And that's the fact I want to end this show on. So, summary. A lot of cool stuff happened in the early universe. The first 3 minutes were very busy. We formed all of the hydrogen, all of the helium, including the part of it that's in your body. We can predict how much of these elements we formed using everything we know about Big Bang and some nuclear physics. Our predictions are perfect for deuterium, helium-3 and helium-4, with slightly off for lithium by a factor 3. We haven't yet figured out why, but scientists are working on it. And it's really cool that this is something that's a prediction that we can measure, and we're almost completely right, just very slightly off. I think it's very cool. Few comments. People talking about sea people who have stolen all the lithium. All that does remind me that I went out birding rather than doing the housework today. Excellent life choice, David. I approve of that. On Friday, I woke up and there was amazing, grey skies and rain, and I wanted to go to the forest, but it was a work day. So I convinced some work colleagues to come to the forest with me, and there's a cafe in the forest, 25-minute walk from my place. And I convinced work colleagues. So on Friday afternoon, we skived off of work and went to the forest to have a coffee and a cake. Excellent life choice. Very much approve of skipping work to go sit in the forest. So that's definitely. So I approve of going out birding rather than doing housework. Okay, people saying that's amazing. I agree. The fact that you're made of stardust and universe dust is amazing. It's also fascinating to realize there's a tiny fraction of those elements that were produced by radioactive decay and are younger than you. Yes, that is always fun to consider, right? Technetium doesn't occur in nature, it's synthesized. Yes, that's why it's not on the periodic table of elements. Is this a Marvel Universe issue? I don't think the Marvel Universe has solved the lithium problem, but maybe in one of the multiverses they did find a solution. Thank you for joining, everyone. Thank you. I see Professor Leaf. Thank you for being here in the meantime. Okay, so this was fun. Lots of cool questions. I think a very cool topic. So thank you, everyone, for joining. As always, it's a good place to end the stream, I think. I should be online next Sunday, but there's a small chance I might have to cancel the stream because I have a conference this week. I'm giving a talk on Friday, and depending how tired I am, I might decide that the weekend is just for doing nothing. Also, I've finally been convinced to try out pole dancing on Sunday morning, and I expect it is going to leave me absolutely exhausted. So there's a high chance that Friday afternoon I'm just going to fall on the sofa and do nothing. But technically, I should be back online Sunday next week. If not, I'll put out a post on Twitter cancelling it, but should be online Sunday next week. Okay, thank you everyone for joining. This has been really, really, really good fun. If you haven't done so yet, please do subscribe, leave a comment, press the like button, all of the usual YouTube things. Viewership has gone down in the last few weeks, so any help promoting the show, shouting about it, pushing it on your neighbours and friends is always appreciated. Thank you everyone for joining. This has been really, really, really fun. I hope to see you all again next week, and I hope in the meantime you all stay safe and take care of each other.